Thanks, Andrea. Hello, everybody. Hello from me. Um, uh, I'll be sitting because I'll be doing a lot of typing, so I hope you don't mind about that. Um, so, yeah, so this last part of this training event is sort of switching gears a bit. So you have probably learned about, within this training, you've learned about how to use like frameworks, like machine learning frameworks that use GPUs, and that's fine. I mean, what you usually use in such cases are frameworks which have already been optimized to run on the GPUs. What we are going to do in this session now, so we have a 3-hour session, so 90 minutes until the coffee break and 90 minutes afterwards, is I'm going to give you a sort of a taste, an introduction of a bit of, at the lower level, how one goes about in actually programming GPUs if one wants to do that. And to do that, I have to talk to you a bit about the GPU architecture. So if you're, so talk about a bit, contrast a bit what the GPU is and what the main differences are compared to the CPU, and a bit about the programming model, right? So how we think about programming these GPUs and what is exposed to us as programmers. And then the main part, so that will be about half an hour of some presentations, of some slides that I want to show you. And that, but the main part of this session, of these 2 sessions, as I said before and after the break, is I will give you some examples of code that we will go through one by one together, that show you how one goes about, as I said, in programming GPUs, okay, at the lowest level. So it helps a lot here if you are familiar with the command line, right? So typing in a terminal. And if you have followed the instructions that were communicated to you in order to get access to the cluster that we will be using, we need to use a cluster because that has the programmable GPUs that I mean, maybe also your laptops have some form of the programmable GPUs, but of course we couldn't require that from you. So that's why we have set up accounts for you on a cluster, which is sort of the same environment for everybody where we can test some of these examples. Okay. So, yeah, so just to repeat a bit what I already said. So the outline of this talk is that there is a sort of lecture part where I will discuss a bit the GPU architecture. And what we will be using is specifically NVIDIA GPUs for this tutorial, which means I have to talk about the specific programming language of NVIDIA GPUs. The other main GPUs that are programmable for scientific computing are AMD GPUs, and a lot of things that I will say map also to those GPUs, but just they use different terminology. And then I would necessarily need to say a bit about the system that we will be using to do our hands-on exercises. And this is what I would like to cover in the practical examples. So we should, by the time you leave here, you should get some practical experience on the difference between how the GPU works and the performance you can get it in and compare it to CPU performance. And we will touch upon the subject of memory coalescing on the GPU and why you need to take care of this and have an understanding of this if you are going to program the GPU. If you don't know what this means here, it will become more apparent in an example. These last bullet points, maybe I run through them quickly depending on how fast we can get over some of the initial examples, okay? And okay, so the assumptions that I'm making, so I assume that you have some familiarity with programming in C or C++, so at least that you can read some C or C++ code, and familiarity with some common features of C, like what arrays look like, how you allocate arrays, what is a pointer, etc. And I also, I mean, I can step you through this if necessary, but it will be help if you, it would help a lot. Or I'm assuming that you have some experience in, you know, connecting to a remote system, editing some files, etc. Via some text-based editor like Emacs or Vim, or by running VS Code on your laptop and using, you know, the feature that allows you to edit files remotely on a server. But even if my assumptions are, these three assumptions are wrong, I hope that this will anyway be useful if you just follow along to capture some of the high-level features of the GPU. So that if you are ever interested in getting into this a bit more for your work, then you can have at least some reference material you can go to. Okay. How you should follow along. There's a repository which probably has been shared with you, where you can find the slides as a PDF, but probably it's easier if you actually go to this URL and load the slides directly in a browser, because then it's easier to copy paste text from a browser rather than from the PDF, okay? So I mean, I'm going to leave the slide now. I'm going to go to the next slide now. So probably what you want to do is type this into your browser right now. I hope it's short enough. So it's sds402.online. That's sds402 is just it's a master's course I teach. That's why I'm reusing this URL /training. And unless something is seriously broken, can somebody just confirm that this works? And yeah, so oh, then my browser for some reason loads it directly, but yes, maybe you need to put a /#1. Why? Well, this one is the 5th, yes, okay. But it starts from the beginning, yeah, okay. Okay. All right. So I'll move on now to the next slide. Maybe you can maybe you can can you put this in the chat? Yeah, maybe just type that in the chat so people can hit it. Okay. All right. So at a very high level, this should be the picture you should sort of have in mind when you when you try to contrast the GPU with the CPU. So if you just bear with me and look just ignore the GPU for the moment and look at the CPU, right? So your laptop, probably the CPUs in your laptop follow this model. CPUs on the server follow this model, but basically you have some cores. These numbers here, 20 cores, are specific for the server with for the system that we're going to use. But in general, you have some number of CPU cores. These cores share a cache, right? And then these are connected to RAM, memory. And I'm ignoring here any storage, network cards, etc. Okay. And so that's the CPU here, is this block. And now if we were to put in the same sort of language, the same sort of block diagram in GPU, then it would look something like this, where you have a lot of cores, but they're not really cores, right? So this SM stands for streaming multiprocessor. Okay, so they're a special kind of core which is optimized for doing parallel floating point operations and other operations in parallel, but doesn't do a lot of the things that the CPU cores do. So that's why you have a lot of them. So each dot here, right, is like another core. These are all these all share, of course, a cache. And then there is GPU memory. On the GPU, there's this own kind of memory that all these GPU cores can read from, okay? So compared to the CPU, more cores, right? But less full-featured, of course. And another thing to note is higher bandwidth to memory. So this GPU memory here, if you can see, I put some numbers here, but these many cores can read from this GPU memory at about 1 terabyte per second, 900 gigabytes per second, which is about, 5 times to 10 times faster than what the CPUs can read from memory, okay? So more cores, faster access to memory, but the GPU memory that is faster is also smaller. So I don't have the numbers here, I have them in the next slide, but usually on one of these compute nodes that we will be running, you have memory which is of the order of hundreds of gigabytes, right? Something like 96 gigabytes or 128 gigabytes. Whereas GPU memory is something like 32 gigabytes or 64 gigabytes, okay? But it's faster. Okay, so those bullet points should are just what I said. So CPU cores are optimized for serial execution, whereas these GPU cores, they are fewer. They're more. Sorry, not fewer. They're more, but they are more optimized for parallel execution and less fully featured than the CPU cores. So these numbers, as I said, they correspond to the actual GPUs that we will be using, which are NVIDIA V100 GPUs, or so-called Volta GPUs. And yeah, those are just some numbers that I also mentioned in the previous slide. So the peak performance, so if you add all the floating point operations that this device here, the GPU, can do in a second, it comes up to about 7.8 teraflops per second double precision, which compared to the CPU, which is usually about 1 teraflop per second is sort of the ballpark performance of the CPU. So I'll come back to these numbers because when we do our examples, we will be comparing the CPU performance with the GPU performance. And so it's good to know, what we're comparing with. Okay, in terms of you as a programmer now that is called to actually make this GPU run your scientific codes or any code for that matter, what are the things you should worry about? So what is the, let's say, model by which you program this GPU? Well, in almost all cases, you use this so-called offload model for the GPU. So offload model means that basically the CPU, so you run your code as any other program, right? The code that you want to run on the GPU is offloaded to the GPU. So you have a program that, like, if you're familiar with Python, you basically have a program like any other program, but then somewhere along the way in your code, you have pieces which you send to the GPU to run, okay? So that's why we call this the offload model. So in C parlance, your CPU runs the main function, and that maps also to Python. If you're more familiar, _ main runs on the CPU, right? The GPU doesn't run this program. Then, because your program starts from the CPU, right? Your program is started from the CPU. Your CPU program does all the memory allocation here, where I'm pointing to now with the cursor, with the mouse pointer. So you're allocating all the memory on RAM, right, which is accessible to the CPU. And then the CPU needs to copy this data, whatever data is necessary to be processed by your program that you want to run on the GPU. You need to explicitly take this piece of memory and move it to GPU memory here over this relatively slow bandwidth of 32 gigabytes per second. Only then is the GPU ready to actually process the data. So then you start launching what we call GPU kernels. So we launched little programs, right, on the GPU that process this data that you've transferred to the GPU memory. And once you're done, then presumably you want to use this data that you have processed, the result of your program on the GPU, you want to use it, either write it to a file or, I don't know, do some additional processing on it. So this needs to be copied back to the CPU, right? So the GPU does not have any access to disk, right? So the GPU cannot write to disk. It cannot, send things over the network. If you want to do any of the stuff that you might be more familiar with when using a CPU, and you need to get the memory, you need to get the data from the GPU memory out into the CPU memory. All right, so that's the offload model. Program starts on CPU, CPU program copies data to GPU, CPU program instructs GPU to run little kernels, and then data is copied back from the GPU to the CPU. Right. You can stop me at any time, by the way. We have plenty of time. You can stop me at any time. And even if you don't have a question and just want me to repeat something, that's perfectly fine with me, okay? Yeah. No, the CPU initiates the copy back from the GPU, but there is mechanisms to say, wait for all kernels to complete before you copy it back, right? But it's exactly, yeah. So so everything is initiated by the CPU on the CPU side, basically. Okay, as a programmer, it's good to know about the memory model of the GPU. Now, I'm going to go back a few slides because what I say here is going to seem a bit contradictory to what I said before. So we said the CPU accesses, just to get some context again, right? So the CPU accesses its memory with about 100, 130 gigabytes per second. Okay, hold that number 100. And that the GPU accesses its memory at about a terabyte per second, right? Okay. So in this picture, this line here is the fastest, right? Compared to this line here, which is how fast the CPU reads from memory. But if you now zoom into the GPU and just look at the GPU, then you see that there is even faster memory within the GPU, okay? So we are going to distinguish between two kinds of memory just focusing on the GPU. So there's so-called global memory and constant and texture memory, which is similar. But then there's also shared memory, which is faster on the GPU. So the different threads, sorry, excuse me. The different threads that you will run on the GPU can have access to both kinds of this memory, okay? It's just that some is faster than the other. So the red ones here, the red memory, is faster than the orange, what I painted orange in this diagram, okay? And another level of organization is that threads are organized into so-called blocks. And what you should remember about what a block is, it's just a grouping of threads, right, which have access to the same shared memory. So the same piece of fast memory, okay? So if all the memory we had was this global memory, then there wouldn't be a point of talking about this grouping of threads, right? Because they all have access to the global memory and they can share data between that orange memory there at the bottom. Okay? But because, right, there is this new hierarchy now, there's this level of shared memory, which is super fast, right? It's an order of magnitude faster than this orange memory. Only some group of threads at any given time can share data between this shared memory. All right. So threads are grouped into blocks is what you should take away from here, and threads within the same block can share through this fast memory. And this shared memory is fast, but it's limited. So for example, on what we're going to use, it's not even a megabyte, right? It's like 96 kilobytes. So it's very limited. It's a very scarce resource on the GPU. Okay, and there is an upper limit on how many threads that you can have that share this shared memory, that live in this block. In this case, it's 1024. And there is just some other limits which are, well, that's just a repetition of what I said before, that this red memory is a very scarce resource, right? This fast memory. Now, these blocks here, right? You can have multiple of them running in parallel, right? So they can run in parallel, these groupings of threads, but you can make no assumptions. You as a programmer cannot make any assumptions about which block runs first and which block runs second, etc. So the GPU just takes care of running these blocks in parallel. What you can be sure about is that within a block, the threads, right, they have some concurrency. So they begin at the same point and the end at the same point, and then they can share that red memory. Okay, any questions up to this point? Fernando.
To what extent do the A100 GPUs have improved? You are showing about V100.
Yes, so the question is, the newer version of GPUs are the A100, and I'm talking about the GPUs that we'll be using in this tutorial, which are V100, and Andreas asked, so what is it that improves? So I think this number is the same, so you can still only have 1024 threads per block, but what increases is the amount of shared memory that you have. What increases is the global memory, right? So I think you can go up to 80 gigabytes now. Other things that increase are the number of streaming multiprocessors increases. And this bandwidth here is faster, so it exceeds a terabyte on A100 per second. So those kind of things. So all the numbers increase basically, except maybe for this one, which stays at 1024. Okay, other questions? Okay. All right, so now I have to talk a bit about the programming model per se, and sort of the workflow in terms of, the GPUs we will be using. So the framework we're going to use is called CUDA, C-U-D-A, which stands for Compute Unified Device Architecture. So this is NVIDIA's sort of higher level solution, although it's not very high level, of how to program these GPUs. So you get a C-like programming language, looks very similar to C, for writing, CUDA kernels and, managing the GPU. So basically you get a compiler which compiles C code, but also understands a few special commands, that are relevant for GPU. There is also some higher level functionality that you can get with CUDA, like you can get linear algebra libraries or random number generators, etc. So the distinction between programming framework and math library sort of blurs, right? Because it's all sort of packaged as, the CUDA SDK. And as I said at the beginning, we will be talking specifically about CUDA here, which is NVIDIA's NVIDIA's framework for programming GPUs. But a lot of these concepts, like the blocks and the shared memory, etc., although they might not have exactly the same names, they also generalize to other frameworks for different kinds of GPUs. Okay, so and the other frameworks could be OpenCL or OpenACC or HIP for AMD GPUs. So those are just some names of sort of competing programming models, competing to CUDA, that would be. Okay, it's good to define these definitions, to say a bit about this terminology, because these are terms that you find in the function names that we're going to use, okay? So whenever you see host, right, that means whatever the CPU is, what's running on the CPU. And whenever you see device, that's the GPU. So a device kernel is something that runs on the GPU. A host function is a function that runs on the CPU, okay? If you want to allocate memory on the GPU, then you call this function, CUDA malloc, in your CPU code. And that reserves memory on the GPU and returns to you a pointer. And this pointer is only good because it points onto GPU memory, right? So it can only be passed to the GPU. So you call this function CUDA malloc, as I said, from the host. it allocates size bytes of memory on the GPU and returns to you in this variable, which I called here dptr, device pointer, stands for device pointer. This is a variable that holds the address to GPU memory though, so it's no good on the CPU, okay? And you can check if this was successfully done by, checking the return value of this function. To release that memory, you call CUDA free with and pass the pointer. Okay, similarly, if you want to copy data from the CPU to the GPU, you have a memcopy function. And what you give it is 2 pointers, right? So the one pointer should be a pointer to GPU memory that you already used CUDA malloc to allocate memory. Whilst the other pointer is a pointer to CPU memory, right? So this is how you would copy an array on the CPU to the GPU memory. And this CUDA memcopy takes a fourth argument. So the third is the size. The fourth argument is the direction. Okay, because you have the same function whether you want to copy from the CPU to the GPU, you have the same function to copy the other way around. You have a flag at the end where you specify the direction. So this says CUDA memcopy host to device. That means copy this data from the CPU to the GPU, whereas you can have the same function. You have the same function to do the exact opposite, which is to bring back data from the device to host, right? Okay. And this is an example of how you write now a function that will run on the GPU. So it looks like any normal C function, but you decorate it with this attribute __global __, which just says this now, it just tells the CUDA compiler that's going to compile this code that this kernel is to be compiled and run eventually on the GPU, okay? But when you come to call this function in your program, in your C program, then, if I were to omit, so these brackets here, these pointy brackets here, they are sort of very non-standard C. This is not C anymore, right? But basically you call the function as if you would normally, but you insert these pointy brackets to signify that this now is to be run on the GPU. And what you specify here is the number of blocks and the number of threads per blocks. So these two should be integers, number of blocks and number of threads per block. And indeed this specifies, right? So if I'm just going back, right. So this tells the GPU how many threads to allocate within a given block, okay, to run this kernel. So how many threads that are going to run this program have a shared memory, can share memory from this red, very fast memory I was talking about before. And how many of these blocks should it use to run, right? And so if you multiply the number of threads per block and the number of blocks, this gives you the total number of threads you're using to run your kernel on the GPU. Okay, these two numbers here. These two can be integers the same way I've put them here, but they can also be not integers, but a group of 3 integers, right? Like a tuple of 3 integers. Because this threads and blocks can be 3-dimensional. But that's something that we're not going to worry about in this tutorial. Just keep it in mind that you can also have this threads per block and this block not only be a one-dimensional integer, but a three dimensions. Now, when you call this function with some number of blocks and some number of threads per block, then inside the kernel, then you have some integers already predefined, as I'm showing here, which give you the position of the thread currently running this kernel, the position of this thread within the block, and the position of the block within all the blocks that are running, okay? So thread idx.x will tell you what the position of this thread what the position of this thread is within all the threads that are running within a given block. Block idx.x tells you which block this thread is running in within all the blocks that you're running. And block dim.x is just another variable that holds the same value as basically n threads here. It's the number of total threads that are running within a block. And this, as I said, can be multidimensional. So here's an example. So let's say I'm going to run my kernel on a grid, which has 4 blocks in the horizontal and 3 blocks in the vertical. So in total, I'm going to run it on 12 blocks. Okay, so it's 4 by 3. And in terms of threads, each block will have 16 by 8 threads. Okay, so if I just look at one block, there's 16 little orange dots in the horizontal and 8 dots in the vertical. Okay. Now, there is a way to uniquely identify each one of these threads, right, in the GPU kernel that you'll run. And that is by getting the dimensions, first of all, so these variables that I'm plotting here on the diagram are variables that you can access within the GPU kernel, which have information about the dimensions of the grid that you're running on. And they also have information about the position of the current thread within the grid. So in terms of dimensions, you will have access if you call your kernel in this way, the way that I've written here, okay? So 4 and 3, I'm just ignoring the third dimension here, or just imagine that that's 1 or something. So you can also have the third dimension, but I won't refer to it here. So just imagine these 2 dimensions. So you have a blocked grid, which is 4 by 3, and that number 4, right, which is the number of blocks in the x direction, will be in this variable, grid dim.x. And the number of blocks in the y direction will be in grid dim.y. Okay. Then the second level of dimensions is what is the number of threads within a block in the x and y direction, and that will be passed to in this block dim.x and block dim.y variables. So that those 4 numbers, right, give you the 2-dimensional dimensions of the grid and the block. Okay, and now any thread that will be running, for example, this is just an example that I've highlighted here, this square here. So any thread that will be running in there will have block idx.y set to 1 and block idx.x set to 2, because the counting starts from 0. So in the X direction, this block is, 0, 1, 2. So it's in the second column. And in terms of the Y dimension, this block is in 0, it's in the first row. So all the threads, there are 16 by 8 threads that will run in here. All of them will have these values for block idx.x and blocks idx.y. And now within that block, right, if I just pick one thread, for example, this one, then that thread will have, that is the only thread within this whole, group of threads that I've highlighted here that has this specific combination of these 4 numbers, right? Because these 2 numbers here, 9, 1, specify the row and the column of this thread within this block, right? So these variables, you need to sort of refer to them inside your kernel in order, if you want to know what position is the currently running thread that is called this kernel. Okay. So that's just a summary of the variables that are available within this kernel. Okay. Yeah, Andrea. It's okay. I can repeat the.
It's just an abstraction. Does it have any mapping
to the hardware? So it depends on the GPU, the extent to which it has. I mean, there is a relevance to the hardware, to the underlying hardware, in terms of the threads that are running within the same block, right? Because we said that those share the same GPU, the same shared memory, right? So all the threads that run within one of these squares will have access to this shared memory, which is red, right? So that is a hardware thing. So this shared memory is something that is in the underlying hardware. Okay. Another thing is that in terms of how the operations are executed by the GPU, okay, the units on the GPU that issue sort of the instructions to the threads, they always issue these instructions to a group of 32 threads, right? This 32 is like a magic number. And these 32 threads that are all issued the same instructions, this warp, so-called warp, it has to always belong to the same block, okay? So there is some mapping of this sort of logical outline to the hardware, but as far as I understand, the sort of the proximity of the different blocks to each other, not really, right? So that's something that you can sort of map.
So maybe if it's you are solving a 2D problem that you have to decompose to a two-dimensional domain, maybe it's more convenient to use a two-dimensional block structure.
Exactly. Yeah. Okay. Yeah, that's how you would do it. Yeah. And then you can decide, which block is neighbor to another block. So this doesn't really have much to do with how their hardware is organized. Yeah. If I change the number of, the question is, if I change the number of blocks. So this is you to choose, right? So how many threads you want to have and how many blocks you want to have is your choice as a programmer. So you map it to the problem that you have to solve, right? Okay, so it's for you. The limits are that the number of threads per block, right? So the number of orange dots within one of these green tiles, let's say, cannot exceed 1024. This is a limit for the specific version of GPU, and other GPUs have similar limits. So there's a limit there. But other than that, you are free to define, you're basically free to, I mean, there are some very high upper limits for the other things, but they're so high you don't need to worry about them. So you are free to use any number of blocks that you want, right? And any way you want to divide them in the two-dimensional. So, you know, there's these numbers here. You can have a 2x2 block. I just gave an example here to sort of explain what these variables mean in this example here. That's all I did. Does that answer your question? Okay. Okay. I don't see the Zoom, so I don't know if there's any question online. Stay here. Stay here. Stay here. He's paying attention. I say I don't have the Zoom, so I don't know if there's any questions online. Okay. Okay. So that brings up, so that's all I wanted to say, you know, as an introduction. Okay. So now we go a bit to the practical, okay? Okay, the operation that I'm going to sort of demonstrate here is a very simple operation, very simple linear algebra operation. But, you know, I've sort of packaged it into a program that I need to give you some, need to explain a bit what I want to do here. So don't worry about these paths because we'll connect later to we'll connect to the cluster in a few minutes, and I'll explain to you how to get the data, how to get the files and everything. But for now, please concentrate on the slide. So the operation, as I said, the operation that we're doing is a very simple linear algebra operation, right? So it's nothing complicated, but it's an example to show you how, you know, how you move such a, as I said, admittedly simple operation to the GPU, how you move this from the CPU code to the GPU and run it on the GPU, also assessing a bit the performance and what actually gives you performance when you do that. So the operation is called an AX plus Y operation, right? So those who are familiar with BLAS, basic linear algebra subroutine BLAS, right? You will know this as an AXP operation, where you basically have two vectors, right? Two long arrays, X and Y, and you add them, but before you add them, you scale X by a scalar, right? So just A times X plus Y, and store the result back in Y. So on a CPU, this is just a loop. It goes from I equals 0 to n minus 1. And, you know, completely point by point addition of two vectors. So the example that we will look at, okay, I'll go over this again, but the example that I'll go over this again when we look at the code. But for now, just the example we will look at implements this on the CPU, right? And it implements it on a CPU in an efficient way. which is just to say that it uses parallelization to parallelize over the CPU cores. You don't need to worry about what I'm doing there. But for those who understand what this means, it uses OpenMP to parallelize over the CPU cores, okay? So we have a fast CPU implementation of this operation. And what I want to do with you is step-by-step port this operation onto the GPU, okay? So step-by-step, take this code and shift this operation, offload the operation to the GPU. So this will mean that we will need to cover allocating memory for these two arrays on the GPU, right? Transferring whatever we need to transfer of the data to the GPU, call the kernels on the GPU, write the kernels for the GPU and call the kernels on the GPU, how to place the threads and how to optimize the memory access, right? And then copy back the data from the GPU to the CPU, okay? This is what we want to do. Okay, this is where I need you to connect to the cluster and copy the exercise to your local folder. So let's do that together. Let me see. So okay, so here is a terminal that is okay. Is that visible? Yeah, you can read the, okay. So this is the terminal on my laptop and okay. I guess you should have gotten instructions on how to do this beforehand. So that's my username, right? And this is the system that you want to connect to. So this should have been given to you in an email where you got training accounts for today, okay? So to connect, you don't need this necessarily. This -AY is, okay, I'll put it away so that you don't need to see that. And it's going to ask me for a password, but I think your accounts were created by the support without a password, so I just need to put my password here. Okay, so now I'm logged into the system, the cluster that we're going to use. And the way I know that I'm logged in is because the host name is changed here to this front 02. Okay, so can we all be here? Who is not? Yeah? Yes? Any negatives? Any no's? All right. There's a lot of time reserved for troubleshooting, so don't feel like if you have any problems, don't feel like you're holding us back, right? Just okay, you're all in it. Okay. This is 100% success rate so far, which I kind of don't believe you, but all right. So once you are here, then okay, this is why I asked you to open these slides in a browser. So you should be able to copy this tree, this path, which is where the exercises are. So I'm just going to list them, ls, to list the exercises. There are 2 exercises. Okay. Do you not have permissions? Okay, so I'm assuming that you are all members of this group. So maybe you're not. Maybe you're not. Ah, but then you should be. Hmm? Yeah. So you should all be able to list these two directories. Can you do that? Yeah, Andrea? Okay, good. That means you have access. Okay. So I have a very messy home directory, but yours should be empty if you have a fresh training account, right? So if you just ls without any arguments, you should get nothing. I have all sorts of crap in there. So I'm just going to, create a directory training. You don't need to do this. And I'm going to cd in there. So now I'm working out of this directory training. Okay. So what I want to do is copy the first exercise, EX01. I have to put a -r because this is a directory. So this will copy all the contents of EX01 to the current directory. I put a dot there. The dot is important. Okay. So if I do, oops, that's not expected. Why is this exceeded? Is it really exceeded? Do you guys get that? Why? Ah, I see why. I see why, because that's my bad. Okay. 23. Okay, can you try it now, please? Sorry about that. Okay, I don't know why I don't know what I did and exceeded my quota, but yeah, okay. So I'll just work off. I'll just work off my Scratch directory. So okay, so there is axpy.q. This is the single file source code that we will be working with, right? Okay, and now is when I will use. So I'm going to be using Emacs to edit this file. Okay, Emacs is a text editor that runs in the terminal. Okay. So if I do Emacs axpy.q, right? C mode. Let me get some colors. Good. So I can, go. So this is the contents of the file, the text file, which is a source code file. I can browse through. I can edit, etc. You don't have to use Emacs. You can also use Vim if you're more familiar with that. I won't judge you for using Vim. Okay. Nobody's perfect, but you can also use, another thing you can do is use Visual Studio I know that there's Visual Studio Code. I know that there's a way. I mean, if you got some info that I gave for the organizational purposes a few days ago, I asked that you are sort of prepared to do this. So if you have Visual Studio, then there is a way to open remotely on a server text files and edit them. Okay. That's what you're doing. Great. Okay. So if anybody needs help, then to do that, then we have at least one person that was successful. Okay. Having said that, I will. Okay. Yes. Okay. I think that's possible. So it just okay. So take some time to read that file, and then just take some time to read the contents of that file, and then we'll also do it together. As I try to get this working here. Stego, what time is the break? Is it at 2:30 or? Oh, it's at 3. Okay. And we. Okay, and okay, sorry for the small delay here. Okay. And line numbers we have. Okay, so I hope you had a bit of a chance to read through the code, but we'll go through it together just so I make sure that I hit the main points, okay? So what we have here is a completely C code, right? There's no GPU stuff in this code. I just called the program axpy.cu rather than C, but that's you know the file name has no reflection on what's inside the code, which is purely C. So in C we have a main program. Here it is. Starts at line 65. Okay. And what we do is we give it one command line argument. So the way we run this code is we run the program, we give it a number, and that number that we give it is basically how big to make these arrays X and Y. Okay. So what it does is it takes this number from this N basically, takes it from, takes it from, you can see that, or it's too dark. I guess that's why it's the use. Okay, I think it's good. What I was saying, okay, so it takes N from the command line, and now it allocates 4 arrays, okay, that are this length. 4 single precision or float arrays that are of size N, and this is basically just a wrapper for the malloc command, okay? So what you see here, ualloc, is just a wrapper for the standard C malloc command. If you're more familiar with C++, this is like new, I guess, right? So this is, I call these X0, X1, and Y0, Y1. And what I do in this loop here is I'm just filling these arrays with random numbers, okay? Just so we're going to do this operation and we don't really care what's inside those arrays, right? This is just for tutorial purposes. So we're just filling them in with random numbers, okay? So X0 and X1 are identical arrays which are filled in with random numbers. So the entries are random, but they're the same. And the same is also for Y, okay? For the 2 arrays Y. Okay, now if you look at these, if I can get it all into one, I can't get it all into one screen. It basically, there's this piece here I call A. Okay, there's this block here that I call A, where this operation here on the slide, AX plus Y, is done, but for the variables X0 and Y0, okay? And then the same is done down here when this piece that I call B, the same is done, but for the variables that I call X1 and Y1. So this is done in this single line here, which is this AX plus Y function. So in this function AX plus Y, I can scroll up and show you what this function does. It's a very simple function. It just loops over I from 0 to N and basically does what's on the slide in code, right? A times xi plus yi. This is also done here. Okay, scrolling back down. Okay, so why am I doing all this? Because I'm going to keep this piece, this A part, I'm going to keep it as it is. But what I'm going to do is I'm going to port this piece to the GPU. Okay, so then we have, you know, it's going to be doing it once on the CPU and once on the GPU. And why do I want to do that? So because at the end, I also want to compare and see that the GPU is doing the same thing as the CPU. So this piece here done at the end is just comparing, you know, the same operation, the result of the same operation on the CPU. Well, At the moment, they're both done on the CPU. Huh? At the moment, they're both done on the CPU, so it's just doing a difference, and it's going to print the difference at the end, and the difference has to be 0 if we got the same result. Okay. Questions? No, anybody want me to, anything not clear, you want me to repeat it? Okay. Okay, both operations are being timed. There's this function called stopwatch, which basically wraps this function in a timer so that it gets the number of seconds that this took. So we're also going to get some timing information of how long it took to run the A part and how long it took to run the B part. Okay. This code will compile and run as it is. It will just not do anything on the GPU, right? Because we haven't done any CUDA yet. So why don't we go ahead and do that together? So I have some instructions to do this. Here on slide here on slide 24, is it? Yeah, the slide with slide number at the bottom right, 24 out of 60. So first, if you can please follow along with me here, I'll do it with you. Let's see if this works. So module, I guess we did this part, right? You copied this code to your directories and you can see the file there. And now we want to compile. So module, first we need to load the right compilers. So first I'm going to module load GOMPI. This is just a module for loading the right C compiler, GNU C compiler, and then module load CUDA will on top of this load the CUDA SDK. And now I'm going to compile this with the NVIDIA compiler, right? So that just means use OpenMP. Well, all of this means use OpenMP. That part there. Output the executable to this name, right? And this is just the optimization level. Okay. If you do that, then a second file. Okay, so this tilde file is just Emacs backup file, so don't worry about that. What you should have is a green highlighted AXPY, so that's the executable program. I guess you can run this here on this node where we're sitting. It'll complain and say you didn't provide the number. So let's put a big number there. Right, so you can put something like 1 million. Is that 1 million? Yeah, that's 1 million. Okay. I'm going to be a bit more fancy and actually do 8 times. What do I say in the slides? 64. So I can actually put 64 million. So this dollar and paren, if you're not familiar with it, dollar and double paren, it just does that. It does that operation inside the brackets on the command line. So it multiplies 64 times 1024 times 1024 and returns the result. So that's just so I don't have to, write 64 on one. Okay. Okay. Okay, but what I'm doing here is something that you should usually not do, because what I'm doing here is I'm running this program on the so-called front-end node. So this cluster has GPU nodes which are connected to a front-end node. So the node that I'm sitting on is this front-end node. That's why its name is front02. Doesn't have any GPUs, okay? So, and also it's shared by all of us now, which are logged in. But what we want to do is send this program to a GPU node to run, even though it doesn't have any GPU code now, it will do later. So that we can do by using this command that I have on the slides here, the last command on this 24th slide. So srun means slurm run, so it's sending the job to a GPU node, and you need all these options because you need to specify that you belong to this training group, which has a reservation on these nodes so that you're given immediately a node to run. Okay, that's why we need all this, all these options here. And so let's see. Yeah, so this now run on this GPU node. And you can already see that it's a bit faster than what you get when you run it on this so-called front-end node, which I did before. So this is the result. Sorry, this is the result of running it on a node, right? So when I run this command, then, you know, a node was reserved for me for the duration of this run, which was just, you know, fractions of a second, but still the system gave me this node, run the code, and brought me back to the front end. Good. Okay. And, oh yeah. So, as I said, when I was explaining, this was the same kernel was run twice. And the difference between the result of the first and the second is 0 because it's just doing exactly the same operation. Okay. Good. And so now what we want to do is start moving parts of this to the GPU. Okay, so we have these two pieces, right? We keep this untouched, but this piece here, we want it to be done on the GPU. Okay, so before I move on to that, I have to make sure that we are all at the same point, right? So have you all successfully compiled and run this code as I instructed using this srun command? Anybody having difficulties? Okay. So then we can move on, yeah? Okay. So I'll take this step by step. And, no, just a note here. Okay, just a note here. So, you know, I included this timing information, as I said before, and the result of this timing. So here on the slide, it says, well, when I was making these slides, it says 90 and 94 gigabytes per second. So this is the speed at which, that's an interesting point. Maybe I can be a bit more explicit about what's, yeah. So I'm going the wrong way. Okay. Okay, so we're only running on the CPU now, right? So what's going on is we're allocating these two arrays in RAM. And by doing this AX plus Y operation, we need to, you know, one by one, move the elements up onto the cores. The cores do the floating point operation, do AXI plus YI, and then they write back the results to Y. So you can imagine as the operation that we're doing as a flow of data from this main memory up to the cores and then down back to main memory, right? And by timing this, how long this takes, right? And by knowing how big my arrays are, I can get an idea of how many gigabytes per second did I sustain in doing this operation, right? And that's what I'm writing in the output there, not there, there, on the command line here. This is this B that I'm writing out, 93 and 100, right? It's not, it fluctuates a bit. So this 100, right, is, in the correct ballpark compared to what I told you is the peak, which is 130. I mean, you're never going to sustain exactly 130 gigabytes per second. You are getting some 80% of that peak, which is about 100 or 90 gigabytes per second, okay? So all that checks out, right? So hardware vendor, Intel tells us the peak is 130, we run it, the simple operation, we time it, we get about 100. So that all checks out. Good. Okay. Right. That's my comment there. Okay. So we're going to use the GPU to replace part B of the calculation. So this is the outline of the steps that we're going to do, and then we're going to do them also in, one by one in the code. So first we need to just include a header file which contains all the definitions. Okay. Then we will add a GPU kernel, which we will call GPU AXPY, which will be similar to the AXPY function that is already written in the code. And then third, we will add a function similar to the function we have, which is allocating the memory. It'll just allocate and check whether the memory's been returned. Okay. And then we will edit inside our main function. We need to allocate arrays on the GPU. We need to copy X1 and Y1 to the GPU, do the GPU AXPY operation, and then copy data back from the GPU to the CPU. Okay, so those are the 4 + 3 7 steps that we're going to make together in the next slides. Okay, so the first step, pretty simple. Add this include file to the top of our C file, like this. Okay. So this is needed because it includes the definitions of the various GPU function, CUDA, functions that we're going to call. Okay, the next one is to define a GPU kernel, right? So we want to keep the CPU kernel, so we're not going to touch that. So we're just going to add a function that is basically the same as the CPU kernel. So if I scroll down to what should now be about line 56, this is the CPU, is the program that runs on the CPU and does this loop, right? We're going to keep that, and we're just going to add another one here. Just copy pasted it from the slides. So this now is decorated with this __ global, right? So that is something I have to put so that CUDA flags it as a GPU kernel, right? But this name is just, it's just my name, right? I could have named it anything, right? So just to be clear, this is just my name, I repeat, but this is necessary for CUDA to know that this will be a GPU kernel. Okay, I'm going to pause a bit to make sure that you're all catching up. Okay. Okay, now, before I do this, I should explain to you what I do here in this ualloc command. Okay. So if you are familiar with C, you will know malloc, which allocates memory. And if you are familiar with C, then you should also know that if malloc fails to allocate the memory that you want, it will not fail. It'll just return to you a null pointer. And then you might continue on your program and try to use this null pointer, and all sorts of demons will jump out of your screen. So all I'm doing here is I'm wrapping this malloc with my own custom function that checks that malloc has not returned null. And if it has returned null, then it exits more gracefully than it would otherwise. Okay, this is all this pattern. This is all this dance is. And I just want to do something similar now for the GPU allocation function. So as we said, we allocate memory on the GPU using a CUDA malloc. And this on the slide 28, what I have here for you is a few lines of code that sort of wrap GPU malloc, CUDA malloc in a function that I call here GPU alloc. Okay, so that's just does memory allocation on the GPU. And if it fails, so if it returns something which is not equivalent to CUDA success, then it exits, as I said, more gracefully than it otherwise would. Okay. So we can hopefully copy and paste that somewhere around line 30. Doesn't matter where you put it as long as it's before main, but it's nice if it's close to ualloc. Yeah. So far, so good, yeah? Good. Very good. Okay, so now we will go into the main program and start. So now we have the functions that we need outside of the main program, but now we actually have to put them together so that this is done on the GPU. And again, what we want to do, again, right? So we boot this program, the GPU is empty, right? So it has no data. I'm scrolling back again because I like to point to this figure, which you've already seen enough of, I know, but so we have the arrays. So far, we have the arrays allocated in CPU memory. Again, what we want to do, allocate memory on the GPU, copy these arrays from the CPU to the GPU, do the AX plus Y operation on the GPU, and copy the data back. This is what we want to implement now in main. Okay. Okay. So here we are. This is the first thing we want to do is allocate the two arrays that we want to pass, right? X and Y. We want to allocate them on the GPU. And now we have this wrapper function, GPU alloc. That we I don't know. Do we want to break now or at 3? I didn't understand what you said before. Okay. Yeah, okay, this might take though 15, 20 minutes, right? Okay. But everybody's so excited, they don't want to go. So they want to go. The catering wants to leave. All right. So I know, don't be sad, everybody, but but we have to take a break. The suit said so. All right.